In this video, I'll be showing 7-segment display multiplexing on the Z80. I was looking at the schematic for my Z80 computer and thinking, how on earth do these segments show different displays? They're all connected in series. Surely if one of the segments turns on, they'll all turn on at the same time, showing the same thing. But I know that they can display different things all at the same time. And that's when I discovered multiplexing. And this is my journey on how I discover what multiplexing is and how it's all software driven. Well, this is the Tech 1F. The segments here are connected in series, although it is showing different characters on the display at the moment, so there must be some multiplexing going on here, but let's prove that they're connected in series. What I'd like to do is now send out a character. Let's send out the character A to the segments here, and let's turn on segments, let's say 1 and 2 and 5 and 6. So in a binary, that will be 1 1 0 0 1 1, which comes down to 33 hex. There are two other data lines here. D6 is connected to the TX line of the serial transmission, and D7 is connected to the speaker. So if you have a look at the code that I'll use, we've got the scan port, which is the port that triggers these segments on and off, is port number 1, and the segment data is connected to port number 2. So what I'll do is load A with 6F, which should light up segments A, B, C, E, F, and G. It will print the letter A. We output it to the segment port. At this point you won't see anything because we have to turn the segments on, and that is done by loading 3.3 to port 1. So I can compile it. Z80 ASM I'm using. It's called example 1 minus out ex1.bin. If I do a hex dump on ex1.bin, I get the mnemonics for the Z80. So 3A and 6F is the load A register with 6F. I can just type that out. It's really simple. So let's do that now. 3E, 6F, D302, 3E, 33, D301, 76. Alright, if I'll restart it back to 2000 address, if I hit go, what we should see is the letter A's on these two segments and these two segments. There we go. If I change the scan port, reset that, and let's try FF, so output it to every port, reset go. AA on everything, and the speaker port is lit up, although it's not oscillating so you don't hear any sound. So how are we going to get this to multiplex? Let's do some theory work now, have a look how they're connected, and let's try to figure out how we can multiplex these displays. This is a 7-segment display. You would have seen this type of display around in clocks, calculators, and even on basketball courts. 7 segments are just light-emitting diodes. And in fact, there's actually 8 of them. 7 for the figure 8 and 1 for the decimal point. That makes 16 pins. These display work by putting power onto those LEDs which light up, and if you light the correct ones up, you might get something useful to see. For instance, the letter A. So we've got 16 pins here. That's a lot of pins. To simplify it, they usually connect the anodes together, or the positive pins of the light-emitting diodes, or the cathodes together, the negative of the light-emitting diodes. Now we've only got 9 pins, and just to even it out, they normally add another one to make it 10. They've named some of the segments A to G and DP for the decimal point. So how are these wired up? We've got 10 pins, and if you want to add another 5 of them, that's 5 times 10, which is 50 pins. That's a lot of pins and data to individually turn on and off those segments. This is really impractical. A much better way to do it is to connect all those 8 pins in series and have the common cathode or common anode turned on and off with some sort of transistor resistor system. So how do we multiplex these? The concept is that we only turn one segment on at a time, displaying the character that is required for that segment. So for instance, if we want to display A, B, C, we'll send the data to the A to G lines for the character A and turn on, let's say, the middle segment. And then we turn it off again. And then we send data to the A to G segment to form the letter B and turn on the next segment. And also for C. And if we do this quick enough, it looks like A, B, C are being displayed. And that's the basis of multiplexing. Send data to all the segments, but only turn one segment on at a time and do it quick enough. Okay, so the concept is that we need to turn each segment on individually at rapid pace on and off. So send a 2 out to this segment, send a 0 to this segment, send a 0 to that segment, and do it quick enough so that it looks like it's a continual read. So let's start with, see if we can get this working by sending out, let's say, the letter C to this segment and letter A to that segment, and switch between them. So here, if you have a look at some code I've got here, just the same port numbers here, and pretty much similar code to what we just did last time. So load A to segment, but this time we'll load it to the second port, which is number 2, so bit number 2 set on, and output it. And then immediately we'll load a C3, which should represent the character C on the segments, to port number 1 this time. And then we just jump back, so jump back to EX2 and just repeat that process. So this should turn them on and then turn the next one on, and vice versa, and just keep going. So let's compile that one. So Z80 ASM ex2.z80 minus output ex2.bin hex dump bin. So 10 lines there. I'll just key that in. So instead of typing this out here, I've got a routine on this system here which I've developed to transfer via serial port, bitbank serial, from my computer to the Tech1F. So if I do Shift 0, SIO in, hit go, I've got to send a start address, so 2000 I want to load it at. And how long is the program? Well, I can look here on the hex dump, it's 12 hex bytes long. So 2012, hit go. Now it's waiting for some data to send. I've got a cool term here which I can send the data to. So let's load a file up, ex2.bin, there it is, and hit OK. It loaded. Perfect. So let's give that a run and see what it will do. So the idea is switch between segment 1 and segment 2 really fast. Hit go. Well, that doesn't look like it's working properly. It's kind of got 88 there, although I'm not sure if you can tell on the screen, but it looks like there's maybe an A and a C together combined. It's just happening, it looks like it's just happening way too fast. I probably need to put some delay in there, like show it for a bit, turn it off, and then show the next one for a bit, turn it off, and then wait, and then repeat the process. So, you know, just turning them on rapidly is just way too fast. Reset that. So let's look at the next bit of code that we can do to optimize this to make it actually work properly. Again, same port numbers. So here we go. We've got loading the letter A to segment 2. But this time we're going to put a pause in. So load the B register with 0. And then I do this jump decrease B not equal to 0. It will decrease B, and when it gets to 0, it will then continue on. Otherwise it will jump to EX3D1, which is the same line. And because B is 0 to start with, it will decrease it first, go to FF, it will be non-zero, so it's basically 256 bytes worth of delay. And then I actually clear out the A, and what I'll do is clear out the scan port, so I'll just turn off all the ports. That might prevent ghosting or other issues. And let's load the second character up now onto port number 1, which is C, do the delay, clear out the port, and then repeat again. So that's example 3. Let's compile that one. So I'll go up arrow, EX3, EX3, compiled, do a hex dump on that. 20 bytes long. Let's serial transport it into the Tech1F, and this is the design of the Tech1F, is that the programming should be done on your computer and then send it to the Tech1F instead of just keying in those hex values, which will only take a while. Do it on your computer, debug it on your computer, send it to the Tech1F via the serial transmission. SO in 2000 start. Now it's a bit bigger, this file, so 2020 is the length. Hit go. Go to my terminal, load up the file, do a file transfer to ex3.bin and activate it. There it is. Alright, so this time here I've got the delay and I've got the segments that switch off. Go, perfect. There we go, we've got AC happening here. So we've basically software controlled the multitasking just on the two segments at the moment. So in theory, I can just copy and paste that bit of code, instead of just for the two segments, use the next four segments as well and fill out all the segments at once. Do reset, kind of like what this is doing here at the moment. So let's look at the example 4. Alright, and then we've got example 4, we've got the A, we've got the B. What we might display this time is A, B, C, D, E, F from left to right. So the first port that I'm going to port output to is 20, which is this one here. And if bit number 5 is on by itself, hex is 20, that's 10, that's 8, that's 4, that's 2, that's 1. And the two spare bits over this side, which we don't use, is 40 and 80, so 80 to the speaker. And as you can see, this is a pretty long bit of code here, hard-coded. Now it's pretty ugly being hard-coded, but let's compile this one and give this a go. So that's example 4. Example 4 compiles it. Let's do a hex dump on this. Let's see how much it's increased in size. Whoa, that's like 5C hex bytes length just to do that, and it's hard coded, but I'm not going to type that out. Let's now load that with our SIO transfer, SIO in, and we go to 205C, hit go to my CoolTerm terminal emulator, go to ex4.bin and hit load. Transmitting, bang, there it goes. Alright, so if I hit go, hopefully we should get A, B, C, D, E, F. Go. Perfect, A, B, C, D, E, F. And that's multiplexing. It's actually not that difficult to do. On the 7 segments, turning them each on and off at rapid succession, and it looks like you've got a constant display of different characters on each screen. With this computer I can slow it down to a different speed, go to a slower speed, and you can see this on the camera now, what it's actually doing. And if I slow the speed of the computer down, you can see it's scrolling from left to right, so from 20 down to 0, turning each character on and off. And if I increase the speed, using this trim pot here, it goes a bit faster. And if I hit 4 megahertz, bang, you can't even notice the difference. But this code is highly inefficient, it's hard coded. I want to see some data there or some information that is saved on the computer in RAM. So if I'm going to think about a better way to do this, let's write down what we need to do so it will make it a lot easier to write the code. So I've got some bit of work I've done here to work out how to program this to multiplex in a much more efficient way. So if you have a look at those bits that we need to turn on and off, we start off with bit number 5, so 0 to 5. That will turn the leftmost segment on, and then we want to turn the next segment on to the one to the right. That's 10 hex, 8 hex, 4 hex, and you can see the bit moves down one at a time. So it looks like we can just do a bit shift here. So we need some way to store the scan bit. And all we do is rotate it one to the right every cycle. And once we move it down to the very end, we can then repeat the process again. So if we look at the bits of what we got on the output scan latch here, this is bit 5 that we want on for the firstmost. This represents 20 hex. And then all we need to do is rotate it one to the right. And then what happens when the bit comes off the end? Well, it kind of depends what rotate you use, but in a lot of the cases, the bit at the end, bit 0, will then go into the carry flag. So we can check the carry flag if we've gone and scanned through all the bits. Once the carry flag has been checked, we either decide whether we continue the process or start again. So if there's no carry, then we just continue to rotate the process 1 byte. But if the carry is set, then we start again. We reset the scan bit to 20 hex. So with a bit of pseudocode, I can kind of worked out what we need to do here. We have some multiplex routine. We set the scan bit to 20 hex, and then we attach the HL register, which is the typical register we use to load data or get data from RAM. We load that to the data we wanted to see. And then what we want to do is just output the contents of HL, whatever that is, the data that represents the LED segments, to port 2. That will turn the that will highlight the particular segments that we want lit up, and then we output the scan bit to port 1. Currently the scan bit's at 20H. Then we need some sort of delay, as we've seen. We need to keep that on for a bit, at least to keep a position so we can see clearly what it is. Then we need to just turn off the scan port, so just blank them all out so it's a clear view of that particular number, no ghosting going on. We rotate, since we've done one scan bit, we now rotate one bit to the right, and we just check the carry. Is it set? No. If it's not set, when we jump back to loop, and we do the procedure again. We get to the next HL. Oops, I was supposed to add in here, move to the next HL value. So move to the HL value, next memory location, loop again, and then repeat the process. Once the carry is set, and then we just jump back to the start. That will reset the scan bit to 20 hex and back to the data to HL. All right, so let's code that out in our Z80. Okay, so we've got the scan bit, the D segment here set up as 1 and 2, start at HL. So what do we want to do? We want to load, let's use B instead of A, because A is going to be used in a lot of places. Let's use B as the scan bit, load B 20 hex. Oops, 20 hex. And we want to point HL to data, so load HL to some data location. So data will be here somewhere. Oh, and I'll just tab them out. So we want some loop here. And then what we want to do is output we want to get the value of HL, so load the contents of HL. And then we send it to the output port, so we say out O2, so that's the LED segments, A. Let's put a space there. Next thing we want to do is load A, B. So that will load the scan bit. And we say out O1, A. So that outputs it to 20 hex. And in fact, O2 can be replaced with these constants here, make it a bit more readable. The scan bit there. Then we need some sort of delay, so load, it's good to use B, it's just a bit more efficient. Load B with 80 hex, let's say. We can always change that. That might change the brightness of the output. The longer it's left on it, I guess it's brighter. The shorter it's left on it, it's dimmer. And then we just, we'll just L1 here, just a simple loop. So D, J, and Z to L1. So that will then just repeat this decrease 80 hex bytes. Now as you can see here we've clobbered B, so B is now gone now. B isn't 20, it's some 0 value by the time here. We need to return that value back. So load B with A. Now where was A last set? A was B last time. So it's the scan bit. So we just save that scan bit. Now we need to XOR A. We'll clear out the segments, the D scan segments, so we'll blank them all off. We should probably move to the next HL location, so increment HL to the next data bit. Now we'll do a rotate right with carry, and we rotate right with carry B. So now this would now move the bit 1 to the right, and if it moves past bit 0, carry will be set. So now we just check for the carry. So jump relative, no carry. We want to go back to the loop because there's more bits to do. So let's have a look here. We jump back up to here. HL is now the next new location, and B is now the new scan bit, which will be 10 now, 10H, 10 hex. But if it's all done and there is a carry, it will continue on down here. So all we want to do is jump relative back to EX5, the start again. And that will reset B, reset HL, and the whole process will repeat. And that's it. So you can see here, much more compact code, way more efficient than what I just did in example 4. Plus we get some variable data, so we're loading the data from memory, and it's about as efficient as possible. Now we need some data here, and let's just cut and paste these 6 bytes, and it should produce the word nice one. All right, let's now compile that. So it's example 5. Let's compile that. I think it's example 5. So Z80 5 hex dump on ex5.bin. Wow, you can see that only 20 bytes long, or 20 hex bytes long, and that includes the data as well. So let's load that up on our system. Reset this. So in, put that one back. I'm going to go to 2020, go to our cool term, load up the file, x5.bin, open, loaded. 06 is load B, so load B 20, that's what we want, and let's go. Nice one. And there you have it. There's how to multiplex 7-segment displays with simple Z80 coding to produce whatever characters you like on here. You can do scrolling text, you can do games. Once you have that scan routine set up, there's a whole bunch of things that you can display on this screen here. But wait, there's more. What happens if you want to multiplex the 7 segments and an 8x8 LED add-on here? And you can see the add-on is actually the same setup as these segments here. Well, maybe you can't see that, but there's 2 latches here, one for the columns and one for the rows. Same with the 2 latches here, one for the segments to turn on and off and one for the LEDs to light on and off. It's actually the same setup, but there's 8 here and there's 6 here. Although there is technically 8 here, there's the transmit bit and the speaker bit. Is it possible to multiplex both the LEDs, the 8x8 LEDs and the segments? Well, yes it is. Now I won't go through this code in detail, but if you look at this bit of code, it's just the same bit of code that we've seen for the multiplexing of the LED 7 segments, but I've got an extra bit of data here. So I've got the LED 8x8 buffer as well. Now in this case here, there is one problem because if I start at port 80 over here, because I've got to go 8 bytes across here but only 6 here, there's a couple of things I've got to do is like skip those 2 there, and it gets a bit messy in the code. So in this bit of code, what I've decided to do is go from the right handmost side, start off at 1 and then move my way up to port 80, and when I get to port 80, instead of turning the speaker bit on, I just ignore that. And because it's happening so fast, you won't even notice the difference. Let's just load this one up and give it a go. First, I have to connect the 8x8. So I'll turn this off. Alright, I've got it connected to ports 6 and 5 here onto the data bus. So this should work. Let's now compile the code. There's 6 and 6. Compiles, do a hex dump of that. Oh, that was 5. Do a hex dump of that. There we go. It's 37 bytes long. Let's load it up. So in start and 2037 go. In my terminal, load up ex6.bin. Alright, we're all ready to go. Let's load it up. Hit go, and we should see some words here and something on the screen. Nice one. You've got a little man going there. That's definitely being multiplexed because you can't produce those type of LEDs on and off without turning each row or column on and off at a time. Perfect. So there you have it. Multiplexing on multiple outputs with some really simple code. I hope you found this video really interesting in terms of what is multiplexing, how to do it, and it really isn't that complicated. And before I get on to my next video, time for some game time, I think. I've loaded up my Space Invader game that I wrote. Let's start playing it. As you can see, being multiplexed at the top and a score down the below, and lives left. Got 2 lives left. It goes a bit fast at the moment. I am going to slow it down for my 4 megahertz. And I lost. Game over. Well, thanks for watching and see you next time.